Hello and welcome to all students. In this lecture, we learn about the differentiation, differentiation and gradient of scalar valued function. In this lecture, we learn about some. We try to solve some examples based on gradient of a scalar valued function. Okay, so outline of our lecture is uh, in the previous lecture we defined what is meant by gradient, then we have taken some examples, remark. Also we studied the algebra of gradient of scalar valued function. Then now in this lecture we study about examples on algebra of gradient, that also we have studied in the previous lecture. Now in this lecture we study about the examples on gradient and Euler's theorem, these 2 points. Okay, so now let us start our lecture. And where is our point? Examples. And we have this thing, definition, and let us take first example. Okay, examples on gradient. Write down question number 1. Find the direction in which the maximum rate of change occurs for the function f of x comma y is equal to 8xy plus 3 times y raised to 4 into x square at point minus 1 comma 1. So first of all we understand the what is problem. What we have to find? We have to find the direction in which the maximum rate of change occurs for the function this. So that direction is nothing but the gradient of that scalar valued function at a given point. Okay, so in this problem just we have to find out gradient of function f at the given point. Okay, that is our direction. Okay, gradient is a vector quantity and the direction of that vector is nothing but the direction in which the maximum rate of change occurs for the function f. And also find the maximum rate of change at that point. And in the next part we will find the maximum rate of change at the given point. So that maximum rate of change is nothing but it is a scalar quantity and it is nothing but the norm of a gradient vector. Okay, so we have to solve this problem into 2 parts. Okay, we write the answer for the function f of x comma y is equal to 8 into xy plus 3y raised to 4x square. The maximum rate of change occurs at point minus 1 comma 1 is given by, and it is given by a gradient of f at point minus 1 comma 1. Okay, so here we have to find out gradient of function f at point minus 1 comma 1. Here we know the definition of gradient of function f at a point, and it is a vector with 2 components. So first component is dou f by dou x at point minus 1 comma 1 comma second component is dou f by dou y at point minus 1 comma 1. So this is our gradient vector. So to find this vector we have to find these two components. Okay, so let us find out these two components. So first of all, we have to find the partial derivative of f with respect to x, means dou f by dou x. So now we find first is dou f by dou x, and it is equal to, means partial derivative of f with respect to x, and it is equal to 8y plus 6y raised to 4 into x. Okay, so function f is given here. Its partial derivative is 8 into x. Its partial derivative with respect to x is 8y plus 6 times y raised to 4 into x. And again we find the partial derivative of f, means dou f by dou y. So dou f by dou y means partial derivative of f with respect to y, and it is equal to 8x plus 12y cube into x square. 12y cube into x square. So dou f by dou y is equal to 8x plus 12y cube into x square. So this is, that step is hidden here. Now we find dou f by dou x at point minus 1 comma 1. So it is equal to, so wherever is x and y in the function dou f by dou x, we put x equal to minus 1 and y equal to 1. So 8 into 1 plus 6 into 1 raised to 4 minus 1 is equal to, answer is 2. And again now find dou f by dou y at point minus 1 comma 1, and it is equal to 8 into minus 1 plus 12 into 1 cube into minus 1 square is equal to 4. So by corollary, the maximum rate of change occurs at point minus 1 comma 1 is given by gradient of f at point minus 1 comma 1, and it is equal to 2 comma 4. So this is the direction, means the along the direction vector 2 comma 4, the maximum rate of change occurs of the function f at point minus 1 comma 1. Now the maximum rate of change is the magnitude of gradient of f at point minus 1 comma 1. Okay, now we find the maximum rate of change is, okay, so maximum rate of change, but it is nothing but the magnitude of gradient of f at point minus 1 comma 1. So the maximum rate of change is nothing but the norm of the vector gradient of f of minus 1 comma 1. That vector is 2 comma 4. Okay, so we find the magnitude of vector gradient of f at minus 1 comma 1. So it is equal to, it is square root of addition of squares of its components. So its components are 2 comma 4, their squares 2 square plus 4 square, and their addition, it is equal to square root of 4 plus 16, and it is equal to square root of 20, and square root 20 is nothing but 2 root 5. Okay, so in this way we can find, in this way we found the magnitude of rate of change in this way we find the maximum rate of change, and also we find the direction vector. Okay, so let us take the question number 2 now. Question number 2, let f be a function and f of x comma y is differentiable at minus 2 comma 2. Okay, f be a function f of x comma y and it is differentiable at point minus 2 comma 1. Let u is equal to 1 comma 2 comma v is equal to minus 2 comma 3 and w is equal to 2 comma 2, and given direction derivative of f at point minus 2 comma 1 in the direction of vector u is equal to 3, and the directional derivative of function f at point minus 2 comma 1 in the direction of vector v is equal to 12. Find directional derivative of f at point minus 2 comma 1 in the direction of vector w. So this is our question. Okay, we write the answer of this question. Let a is equal to minus 2 comma 1, therefore du f of a is equal to 3 and dv f of a is equal to 12 and dw f of minus 2 comma 1. So we have to find dw f of minus 2 comma 1, means we have to find this directional derivative. Okay, we know the relation between directional derivatives and gradient. Okay, do you know the relation? We write the relation here. So consider this relation and we solve this step by step. So relation is du f of a is equal to grad f of a dot product with vector u. This is the relation, and in this relation on the right hand side we write the value of gradient of f at point a. It is nothing but a vector with two components, fx at a comma fy at a, means fx at a comma fy at a, and dot product with vector u, and u vector is 1 comma 2. It is equal to fx at a. Now if I take a dot product of these two vectors, we get a scalar quantity fx at a plus 2 times fy at a. So fx and fy, they are denoting the partial derivative of f with respect to x and y respectively. Okay, so du f of a is equal to fx at a plus 2 times fy at a, but du f of a is given to you. Du f of a is 3. So on the next slide or on the next step, du f of a is equal to fx at a plus 2 times fy at a, and this implies 3 is equal to fx at a plus 2 times fy at a. So we have the first equation here. Again consider the relation between directional derivative and gradient like this. dv f of a is equal to gradient of f at a dot product with vector v. In the next step, we write the definition of gradient of f at point A. So fx at a comma fy at a dot product with vector minus 2 comma 3, and it is equal to minus 2 fx at a plus 3 fy at a. So thus we have dv f of a is equal to minus 2 fx at a plus 3 times fy at a, and this implies that the value of dv f of a is 12, and it is equal to minus 2 times fx at a plus 3 times fy at a. Now we consider the equation 1. 3 is equal to fx at a plus 2 times fy at a, and second equation is 12 is equal to minus 2 fx at a plus 3 fy at a. So now to solve these two equations, multiply equation 1 by 2 and add the resultant equation in equation number 2. We get, so multiply, if we multiply to the equation 1 by 2, then the resultant equation is 6 is equal to 2 fx at a plus 4 fy at a. Now we write the second equation below this equation. 12 is equal to minus 2 fx at a plus 3 times fy at a. This implies, if we take the addition of these two equations, so minus 2 fx at a and plus 2 fx at a will get cancelled, and we get on the left hand side 18 is equal to, on the right hand side it is 7 times fy at a. So finally fy at a is equal to 18 upon 7. So this is the value of one partial derivative, and that value is here. Okay, so fy at a is equal to 18 upon 7. Now put the value of fy at a in any one of the above equation. So we get fx at a is equal to minus 15 upon 7. Thus we have the values of partial derivative at point A. So first value is this and second value is this. Okay, so these are the two values of partial derivatives. Fx at a is minus 15 upon 7 and fy at a is 18 upon is 18 upon 7. Okay, now we can write the gradient of f at point A. Okay, now on the next step, now we find now we find dwf at a. dwf at a means it is nothing but the directional derivative of f at point A in the direction of w, and we know that it is equal to gradient of f at a dot product with w. So this is nothing but the relation between directional derivative and gradient of a vector. Okay, so in the next step we write the definition of gradient. Fx at a comma fy at a dot product with vector w is 2 comma 2, and if we take the dot product with this vector we get the what we get is a scalar quantity 2 times fx at a plus 2 times fy at a. It is equal to 2 into minus 15 upon 7 plus 2 into 18 upon 7. So if we solve this thing we get minus 30 upon 7 plus 36 upon 7, and finally we get 6 upon 7. So dwf at a is 6 upon 7. Okay, so in this way the directional derivative of function f at point A in the direction of vector w is nothing but 6 upon 7. So directional derivative is, it is a scalar quantity, so it is a scalar number 6 upon 7. Okay, and okay, now for any query you can contact on this, and we stop our lecture here. Thank you very much.